In this last example, we've got a block sliding down a frictionless ramp and landing on a spring below. So we're going to analyze this system in a couple of example questions. A 425 gram block is released on the frictionless 85 centimeter high ramp shown below. At the bottom of the ramp, an ideal spring is attached to a wall. The spring constant is 94.3 newtons per meter. A, how fast will the block be traveling at the bottom of the ramp? So first of all, we've got a little diagram for ourselves to start. So some of the things we're given, we can call this point 1, since this is the release height of the box, and I can call that H1, and it's released at 85 centimeters, so 0.85 meters. It's initially released from rest, and it slides down the ramp. So the first point we're interested in is this one, point 2, right at the bottom of the ramp. So to start the problem off, the total energy at point 1 has to be equal to the total energy at point 2. At point 1, I'm going to have some combination of gravitational and kinetic energy. At point 2, same thing, since the spring hasn't really entered into it yet. Then I'll take a look at that equation and say it's not moving initially, so there's no initial kinetic energy. I'm also going to decide that this ground level will be my reference height, h equals 0. So that means that at the bottom, point 2, it has no gravitational potential energy. So this equation is going to turn out to be pretty easy to solve. mgh1 is equal to 1/2 mv2 squared, and I'm just solving for v2. In this case, I didn't even need the mass for this part A question because it divides out of both sides. So in this case, to rearrange, V2 is equal to 2gh1, and I got to take the square root of both sides of that equation. In this case, I've got 2 times 9.81 times my original release height, which was 0.85 meters. Since I'm dealing with just 2 significant figures in my final answer, I'm going to go ahead and evaluate this in one step. And I get this number, 4.0837 meters per second, rounded to 2 significant figures. So the speed of the block at the bottom is 4.1 meters per second. Now on to part B. At the bottom of the ramp, the block slides along this surface for a little while until it compresses a spring. And part B asks, what is the maximum compression of that spring? So let's pretend here's the box. Look, got a little taller, oops. And here's the spring once it's compressed at its maximum compression. So at this moment, one thing to notice is it's still at ground level. It has no gravitational potential energy. If it's maximally compressing the spring, it has stopped moving instantaneously, so it has no kinetic energy at this point. In fact, the only form of mechanical energy it has at this point is elastic potential energy. So I'm going to again compare point 1. I know information at point 2, but it's not a bad habit to get into to compare information that you're given, especially in a multi-step question. So at point 3, maybe I could have kinetic and gravitational potential energy. I'm just going to show all of my steps. But now I'm going to look at that and I'm going to say initially, oops, I'm sorry, this would be a 1. Talking right at the same time. Initially, it has no kinetic energy. In the end, it's at our reference height. It has no gravitational potential energy. It's stopped. It has no kinetic energy. It only has elastic potential energy. So gravitational potential energy to begin with is mgh1. Elastic potential energy at the end is 1/2 k delta x squared. Keeping in mind, I've got to convert everything, all of my delta x's to meters. Heights are in meters, masses are in kilograms. I would like to solve for delta x without the squared. So I'm going to rearrange by multiplying both sides by 2, dividing both sides by k, and taking the square root of both sides in order to rearrange for delta x. So now I'm going to substitute in my numbers. The mass was 425 grams, but I need that to be in kilograms. Not a bad idea to show this as a separate step, which I'm not. The height is 0.85 meters, and I'm going to divide that by the spring constant, which is 94.3 newtons per meter. And that's equal to delta x. Oops. Doesn't really want to go down that far. There we go. So in my numerator, actually, I'm not even going to do that because this is a one-step question. Everything is multiplied or divided. In this case, my least precise number has 2 significant figures. So my very last number, which I'll plug directly into my calculator, ends up being 0.274156. I'm going to round to 2 significant figures. And I'll write, therefore, the maximum compression of the spring is 27 centimeters. Part C, last step. How far back up the ramp, and I want the distance traveled, not the height, will the block be when it has a speed of 1.9 meters per second? So here, let's call this point 4. It's going to be some height up the ramp, and I want to know what is this distance, d. I'm also going to need to figure out as part of my solution, what is that height for that corresponds, and I'll call that, let's call that d4, with distance 4. So here, again, spring energy doesn't enter into it, but I will have some combination of gravitational potential energy and kinetic energy. So part C. The total energy at point 1, which is what I was given, still equal to the total energy at point 4, since I have nice frictionless surfaces, no losses there. I've got some gravitational, kinetic possible energy to begin with. Partway up the ramp, I'm going to have some possible kinetic energy. Oops, and I'm using the wrong subscript already. Kinetic energy, gravitational energy as well. Except when I take a look at this, I know, of course, initially I have no kinetic energy to begin with. So mgh1, total energy in our system, is equal to mgh4, which is the gravitational potential energy of the block when it's partway up the ramp, plus 1/2 mv4 squared, which is the kinetic energy of the block when it's partway up the ramp. In this equation, I don't have any springs. All of my terms involve mass, so I can divide mass by both sides of my equation, which simplifies things a little bit for me. I would like to rearrange for h4. Not my final answer, but it's partway to get to my final answer. So I'm going to rearrange gh1 subtract 1/2 v4 squared equals g times h4. So to rearrange this equation, I have gh1 subtract 1/2 v4 squared divided by g. Now I just need to substitute in some numbers. 9.81 times the original height, 0.85 meters, subtract 1/2 times the speed at 0.4, which was 1.9 squared, divided by 9.81. That's equal to h4. So now I'm going to simplify this one step at a time. The first term will be equal to 8.3385. I know that to 2 significant figures. Subtract the second term, which is equal to 1.805. And again, I'm only dealing with 2 significant figures, divided by 9.81. The numerator simplifies to 6.5335, 2 significant figures again, which is actually just 0.666, did not do that on purpose, 04 meters. Now, this isn't quite what I was asked to find in this question. I was actually asked to find the distance up the ramp, not the height. Here's H4. Here's the distance it's traveled up the ramp. But there's one other piece of information that's going to help me, and that's the angle of the ramp. It's 21.3 degrees. So all I really need is some trigonometry to figure this out. Oh, and I forgot to put a little arrow here, 2 significant figures. Since I'm dealing with this angle, an opposite side, and the hypotenuse, I'm going to need to use sine trig ratio. The opposite side was H4, the hypotenuse was D4. So when I'm solving for D4, that's equal to H4 divided by sine theta. H4, 0.666004 divided by sine of 21.3. My final answer will have 2 significant figures, and that answer ends up being 1.833 meters, so rounding to 1.8 meters. Therefore, the block will be 1.8 meters up the ramp at this time.